Hello, welcome again to the other part of the other parts of linear programming. Okay, so this one is series two. Okay, so in linear programming series one, we already discussed in detail, in depth about how can we find the optimal solutions. All right, based from finding using graph, and we can find our curve, all right, and then later level curve, and then later we can get the optimal values, and by having the optimal values then we can proceed to find the z, right, the objective functions. Okay, the optimal objective function. Now we proceed to see what are other different kind of linear programming that we have. Okay, is it all situation we have an easy solutions, or by the end of the day do we always have the two different linear function that link together and just nicely we get the points. Okay, is that always the same situation? Okay, so this is some of the examples how there are other different kind of problems that sometimes does not give the exact value that we want. Okay, so and if let's say that thing happens, how can we get the value, and what is it, what else can we do to get the value that we want? Okay, so these are the example. Earlier we touch on especially on the maximum values. Okay, now we try to find the minimum value, the optimized solution, but this one in a minimum value. What will happen to the level curves? Do we still increase it on the right hand side, or are we going to decrease it to the lower level? Okay, and see what happens. This is an example. Let's say you have a minimum cost. Okay, but again, I need to remind again that normally when we have a linear programming, we are dealing with problems. Okay, problems meaning that a lengthy sentences put together. But since we are trying to find the solution, we are trying to expose on different kind of solutions. So I just show you here, okay, examples that is already in a mathematical forms. Okay, but you always have to remember before we proceed with the mathematical form here, normally we are involved with different kind of problems. Okay, normally real world application, real life problems. Okay, so it is not just as simple as you having this mathematical formulation cater for you, and then you solve it. It's not like that. Okay, so you need to identify your constraint, you need to utilize your objective function and so on. Okay, so this is the example of maximizing cost, and you have one, two, three, four, five different constraints put together. And then once you translate all your constraint into a graph, okay, you can see over here. All right, this is the constraint function that you have now. Okay, so in this case, you can see over here, you have five different, one, two, three, four. Okay, you have four different linear line put together in one segment. So now you can see your feasible solution. In this case is like this. Okay, another one. Okay, I'll show you earlier. For example, like this one, as mentioned earlier. This one just meaning that you utilize your values in the first quadrant. Okay, the plus plus quadrant. Okay, so okay, this is what you have. All right. So when you have this, okay, when you try to find your level curve here, okay, so your level curve now is this. Okay, this is your first level curve. Okay, so meaning that you try to just find the constant value for your objective function, and then you try to uh, make sure that you already have your slope for your linear line, so you more or less know where your value for your level curve is there. Okay, and then you go down because we are trying to find the minimum points. Okay, so meaning that you go down your level curve over here. That's why you have this up until this point. You can see now your level curve over here. We call this actually an isoprofit. Okay, so once we have this line over here, you can see, oh, this is your optimal solution here. Okay, so that one is clear. You can see over here, because this one is not yet your optimal cost, because you can still reduce your level curve downward until you get this. Okay, so I highlight again. I highlight again this optimal solution over here. Okay, so once you get the optimal solution, the rest is just follow as how we solved in the previous example. Okay, now we proceed to another example. Okay, let's say now your example over here, you have a maximum objective functions, and then you have all the subject to meaning that all your constraints over here. We still focus on our first quadrant, and then we see the value over here now. Okay, this is another way of you to solve your objective function, finding your optimal solution but not using your level curve anymore. Okay, how to do just that? Okay, this one, there are plus and minus part of it. Okay, the plus part of it is that you don't have to uh, construct your level curve. Okay, but the negative side of it is that you have to do many times the calculation of your values. Okay, so what I said that, okay, in this case, you just find, you have to make sure once you have the feasible regions, okay, whatever it is, you need to make sure that you already find your feasible region. Once you find the feasible region, you need to make sure that you identify mm, all your corner points. Okay, so in this case, this is your corner point. This is why it makes a little bit tricky here, because normally sometimes people do forget that the value over here is a corner point. So you're very easily uh, get sometimes you get disturbed with this particular information, because you always focus on the linear line that is intersect with each other. So normally D should be okay. But A, B, and E, normally people mix them together. Okay, so that is the danger of having this kind of methods. Okay, but it still work. All right, it still work. So once you already identify all your corner points, okay, using this particular method, you put all your corner points, meaning that your corner point now must have your coordinate, right? So you have so you have your x and also your y. Okay, so you put your coordinate, okay, x1 or x2 doesn't matter, inside your objective function. And then you calculate one by one. So in this case, this is the value for your objective function correspond to your value of your coordinate on your corner points. Okay, so correspond meaning that your A, it resulting to your objective function, which is 0, the B 3000, and so on. Okay, so from this you identify which value that give you the most optimum one, because you are trying to find the maximum value. So in this case, you find the maximum value. In this case, you have 3800. So you correspond your 3800 with your value, optimal value for your x1 and x2. So it's 6040. All right, your 6040, meaning that this one. Okay, so this is your C. All right, so this is actually your optimal solution. Optimal values that will give you your optimal solution for your objective function. Okay, so this one, some people like this approach. Some people like the level curve or isoprofit method more. Actually, it depends on yourself. Okay, there's no right or wrong answer. Okay, now this example, you can revisit this example if you want to know a little bit more. But by the end of the day, what I want to focus on is the solution here. You look at these solutions. Okay, you imagine this solution is comes from the previous constraint that you have. Okay, now in this case, okay, you can see that your feasible region now is a little bit different. Okay, now your feasible region, since you are having a linear line or constraint that is over here, and your another constraint is also over here, and then the rest is just the same. For example, is on the first quadrant and so on. Okay, and then you can see how can you get the feasible solution if you want to get the maximum values. And then if this one is your level curve, okay, or your isoprofit, okay, value. So let's say this is your level curve, and then how are you able to move forward there? You cannot, right? Because this one is unbounded. Okay, you cannot find the intersection between two lines together. So this is the example of you're not going, you are not able to find your optimal solution by using your linear programming. In this case, you need to retweaks or readjust your solutions, how you're going to readjust that to at least get the optimal solution that you want. Okay, so there are other methods involved. And it needs a lot of different ways to solve this. All right, but in this particular notation, I'm going to just I want to highlight to you different scenario of your particular linear programming. Okay, these are some of the examples, different cases that may result in your solving your linear programming problems. All right. Okay, so you can see over here from based from my previous explanation earlier. Okay, I highlighted two different methods. The first one is isoprofit, which involve with the level curves, and then your level curve must go upward if you are trying to find the maximum value. And on the counterparts, okay, you need to reduce or you need to decrease your level curve to the downward position if you want to find your minimum or decreasing cost. But whatever it is, your slope must be the same. Okay, yeah, just the position of your level curve is different, but your slope is always the same. You always have to remember that. And then the next method is about the corner point method, whereby you need to find all the corner points, and then based from your corner point, you put your value on your corner point to get all the corresponding objective functions. Okay, once you get the objective function, you compute that, you find whatever solution you may want. Okay, for example, maximum, you find the maximum value for your objective function. If you want the minimum one, you identify the minimum value for your objective function, then that is your optimal solutions for your problem in hand. Okay, so these are the basic assumption for your linear programming. You need to identify that it has the certainty. Okay, what does it mean by certainty? I think you know the certainty. The proportionality. Okay, I need to highlight a little bit on the proportionality. It means that uh, there exists the proportion part. Okay, proportion meaning that if let's say to make things simpler, if let's say you have y equals to mx. Okay, it's a simple linear function, but you notice that it has the proportion between your variable y and also variable x, right? Meaning that if let's say I increase my x depending on my m, my slope, I will get an increase on my y. If I multiply my x, okay, with 3, okay, definitely I will increase my level of quantity in my Y three times of my X, right? So that is the meaning of proportionality. Okay, so that's how you get it. Means that if 1 unit of a product uses 3 hours of a particular scarce resources, then you can imagine if you are making 10 units, then by right you will use 30 hours of resources. That makes sense, right? Okay, so that is the meaning of proportionality, and it has to become one of the basic assumption of your LP. And then your additivity and your divisibility is just the same. Simple concept. All right. Okay. So these are some of the special case. Okay, special case about some of the cases. Sometimes you find it when you solve your linear programming. Okay, our previous example, Gia, Peto, and also Dorian is just a straightforward example, meaning that you have a unique optimal solutions. Okay, some LP they do not have a unique solution. Okay, sometimes they have infinite number of solutions. Okay, I will show you in the example later. And then some of it you cannot use your linear programming or whatsoever. You need to adjust a little bit. What about if, let's say, you don't have any feasible solutions? That is also tricky. All right. So, how to move about? Okay. So it is possible. Unfeasible. There are also example later. What else? Some of the LP are unbounded. Unbounded meaning that your feasible region is way out of hand. Okay, for example, on the earlier case we noticed just now, that one you have also to uh, tweak a little bit and that, and sometimes you need to make sure that you have to have another level of making decisions. Sometimes it involves with people's experience and so on. Okay, so we see example. One of the example of the alternative optimal solutions. If let's say you have this example. Okay, and then you transfer it into a graph form. Okay, you can see over here in this graph, you can see in this graph, it has an infinite number of solution. Okay, what does it mean by that? Okay, you look carefully about the isoprofit or the level curve. Okay, your level curve is in the dotted line over here. All right, so your dotted line over here, this one, eh? Okay, you notice your dotted line. If you move it over here, you want to find the maximum value for your problems, and then suddenly you notice it will merge into your it will merge into your line over here. All right, so actually it will merge into your line AB. AB, but we don't care about EB, right? Because EB is not in the feasible solutions, but we cannot ignore our AE. Our AE is part of the feasible solutions. So in this case, you notice this is a continuous points, right? All these are the solutions over here. All right. So this is what we call an infinite number of solutions. There are lots of solutions that you can say this is part of the optimal solutions for your particular problem. So that does not make sense, right? How can you make sure, okay, which is my optimal solutions, because I have a lot of different solutions. So which one should I choose? Okay, that is when you need to find another way. Now we are talking about, for example, judgment. Okay, judgment. What we call that? But basically it based on human judgment. Okay, so that's why we put for example like this point. Okay, the manager might prefer point A, but then you need to once you put your qualitative judgment. Okay, qualitative judgment meaning that decision making that is not based on the quantitative methods. All right, so you need to justify a little bit more. Okay, why you select this point? Why you're not selecting E or why you don't select point over here. Okay, you maybe wonder, okay, what is so significant about the points? Okay, you always have to refer back to the linear programming's concept. All these points representing the, for example, the quantity of the unit that you're going to produce. Okay, when you put it in that perspective, you might understand the importance of having to make a good judgment. Because if let's say your x1, for example, now in a 100 times, okay, so basically from this point and this point, even though you look at the scale is quite small, but when you consider the production of your profit, it's completely different. Okay, from one point to one point, maybe the difference of the output will involve 1000. Okay, you produce one unit of you produce 1000 unit of phone, for example, is not the same as producing 2000 unit of phone. It involves with different cost cutting, it involves with different kind of resources that you need to pull through, so that is why it is important. If let's say this happen, and if let's say you need to make a human judgment or judgment based on human decision making, then you need to make sure your judgment is based from at least a justifiable cause or means. All right, it's not just an impulsive reasonings, okay, which we don't do normally for an analyst. All right, so that makes sense, right? Okay, now we try to see this kind of example. This is an example where you have the infeasible linear programming. Okay, so when we translate this into a graph, this is the graph that you will have. There is no feasible region. Okay, earlier you have feasible region, but you have infinite solutions. But here in this case, you cannot get any feasible regions. So what should we do? Something like that. So this is a type of the example, different kind of alternative example, not a one size fits all solutions. All right. So this is the example of the unbounded linear programming. All right. So you have two line put together, and then it's bound indefinitely. And then if you put your isoprofit line or your level curve, and then you move further and further, you cannot find the solutions whatsoever. Okay, so this is one of the examples as well. Okay, so by the end of the day, I would like to conclude for this particular part. Okay, if let's say you have two variables, okay, easier. Okay, if let's say you have more than two variable, that is another story. We need to find another method to solve that, and normally we are trying to use it to solve it by using a machine. Okay, but if let's say you have two variables, okay, it has to fall into four different case. It's either you have a unique optimal solution, which is something like a blast. We would really love to have a unique optimal solutions. Or you can have multiple optimal solutions. Okay, it has two or more extreme points. Okay, this kind of linear programming will have an infinite number of optimal solutions. Okay, this one as I mentioned earlier. And then if let's say your linear programming is infeasible, okay, you cannot find any point that is feasible at all, or it's either your LP is unbounded. Unbounded meaning as the latest example that I showed just now. All right, so I leave you with this exercise. If you look at the assumption four, assumption that I mentioned earlier, okay, assumption about, for example, proportionality, additivity, division, one more I cannot remember earlier. So look back at the Giappetto problem and also the Dorian. Does these two example meet these four assumptions? Okay, you think about it through and you can let us know in your comment. Okay, so I hope you enjoy this two-part video. Okay, I'll see you in the next part. Okay, later. In the later slots. All right. All the best. Assalamualaikum.